Hey guys. Okay, so before we get started today, I just wanted to make sure you guys all had were able to see and get access to the stuff I posted online yesterday. I sent out an announcement about things like homework solutions that were put up on a homework module, like a separate little module, and then also the final midterm exam stuff that's in next week's module, all those practice things, in addition to all of the homework detailed solutions that I put up yesterday for different pieces of chapter 2.4 and 2.5. Let me know if you can't access those things. I've been, Canvas is like, I guess they're tweaking it behind the scenes. They're changing some stuff. And then, so it looks like some of the things that like files that I've uploaded sometimes will be there in the file directory, but the links to them on our page will be non-existent. So if you go to access these things and they're not there, please let me know right away so I can fix it, or at least find out what's going on. Okay, so you guys should be able to see all that stuff that's just newly posted up there. That should help clarify some things. And give me just a second. There. Okay. Don't forget, homework that's due today is chapter 2.4 and 2.5. We have a quiz on those two chapter sections that's opening up at noon today. It'll go from noon today to noon tomorrow. You guys can take that quiz, and then the homework is due at midnight tonight. I can't think of anything else. Let's see. Also, don't forget too that we have a midterm exam coming up in a week. So the stuff that we're doing, 2.6, 2.7, and then 2.8 material that we'll cover on Monday will all be on, I'll be due on Thursday when we have our exam, our midterm exam. Okay. Oh, there. All right. All right. So today we're doing chapter 2.7. There. So chapter 2.7. We're starting our discussion of trig functions. Today we're talking about sine and cosine. Okay, some of this stuff should be hopefully a review, and then we're going to start applying calculus ideas to it. Okay, so we're going to do a little bit of a review of things that maybe you covered in high school. Hopefully you covered them in high school, in a pre-calc class or an algebra 2 class. So sine and cosine, let's just go ahead and jump right in. Sine and cosine are really interesting, unique functions. They're sort of elementary functions that basically describe, in combination with e to the x and ln and all that, they describe so much about our natural world. These are considered periodic functions, which means that there's a pattern to them. Like you can think about your generic sine equation, right? And then it goes off like this. So there's a pattern to them that basically from here to here, right, this, you know, kind of curving up, curving down pattern, that pattern repeats itself over and over and over again, okay? So then this here is the period, the time it takes, you know, the time it takes to complete one whole cycle of this design essentially is considered the period of the function. And then it repeats itself again and again and again for infinity, right? So periodic functions, they have this repetition, this cycle that they repeat themselves. Okay, there's a whole like definition with a lot of like extraneous words in it that I'm cutting down, okay, so that kind of save us some time. But they're essentially sine and cosine are periodic functions. Okay, one of the things, I'm going to write this in red, that's really important. One of the things I want to point out too is that all angles are in radians. Okay, so make sure, you know, when you're working with stuff in this class, Calc 2, all these math classes, we're all dealing with radians. Okay, so if you conceptualize things in degrees, make sure you get in the habit of thinking about what they are in radians, because all the answers and everything that we plot out is going to be in radians. All right, so let's just do a quick review of some of our trig stuff. So we're going to first talk about our unit circle, which is where our periodic functions come from, right? Our sine and cosine, basically this is we're unwrapping a circle essentially onto our axis here. Let's see if I can draw this out as a nice circle shape. It's kind of wobbly. All right. Okay, so we call this a unit circle because it has a radius which is equal to 1 unit. Our radius r is 1 unit. Okay, which this is also, this here is our radius here. This is equal to 1 unit. This is our radius here, that's 1. This is also 1 unit too in terms of its magnitude, but in terms of the quadrants, right? This is our x, this is our y-axis. This is a negative x-axis. Right here, we're dealing with a negative y-axis, but the radius, the magnitude itself is still equal to 1. Now, if I drop down and I make this radius, I think about that as having an angle with the x-axis, my theta, right? I can basically think about, I've got any point x, y along that circumference of my circle, okay? So if you think about, I've gone out x in this direction and I've gone up y in that direction, and I'm writing really small here, y in that direction. If I think about my right angle trigonometry, right? So cosine of theta equals adjacent over hypotenuse, x over r, but our r is equal to 1, it's equal to 1. So basically our x is equal to our cosine of theta. Okay, it's a nice thing on our unit circle. Then if I think about, again, my sine of theta is my opposite over hypotenuse, right? But again, our radius is equal to 1, right? So then our y is our sine of theta. So any particular point along this axis is basically represented by cosine of theta, sine of theta. That can give me a coordinate along this axis. And it's nice because now, instead of having to deal with x and y, I'm basically down to one parameter, my theta, my angle, as I go around this circle here. Okay, so it's pretty powerful. Now also our sine and cosine values, right, as I go around this circle, our sine and cosine values are going to be dominated by, is the x positive or negative in this quadrant, right? Is the y positive or negative in this quadrant? And that's going to tell me, you know, what's happening as I progress around this circle. Okay. In terms of angles, angle measures, so we start off at 0 radians, and we've gone pi over 2 radians. Right here, we've gone pi radians. At that point, we've gone 3 pi over 2 radians, and full circle, we've gone 2 pi radians. It's a circle, so I can keep traversing it over and over again. We tend to progress in the counterclockwise, is considered a positive angle direction. But I could just as easily go negative, right? Which means I'm going to go in this direction here, which is why my sine function repeats itself as I go along. I'll draw out my cosine function here as well. So cosine here, here, there it goes, something like, then it repeats itself here. Okay, so my cosine, let's write this is our cosine. This is our sine in blue and red. We'll come back to that graph in just a minute. So just in your mind's eye, and also just, you know, on paper or whatever, if you want to convert back and forth between radians and degree measure, you want to remember the proportion. So 2 pi radians, that's going full circle around, is equal to 360 degrees. So then I can say, well, if 2 pi radians is equal to 360 degrees, then x radians is equal to 75 degrees or 130 degrees or some degrees. Right, so depending on what I'm converting back and forth between from radians to degrees, this would be something I'd fill in and I'd solve for that, right? Or this would be something I'd fill in and I'd solve for that. But 2 pi radians equals 360 forms the basis for our proportion to convert. Okay, hopefully this is a review. All right, so let's talk about some properties. This should also be a review too. Properties of sine and cosine. Okay. So our most basic fundamental trig identity is the Pythagorean identity. I'll write down super important and fundamental. Right, and it comes basically from our Pythagorean theorem. So sine squared of theta plus cosine squared of theta equals 1. Okay, so if you think about our Pythagorean theorem says a squared plus b squared equals c squared, right? But in this case, this side here is equal to the cosine of theta. This side here is equal to the sine of theta. And then our radius, right, our hypotenuse is equal to 1. So, right, this is a squared plus b squared equals c squared here. So our fundamental identity is Pythagorean identity. We use this a lot to simplify, longer chains of expressions. We can also derive 2 more Pythagorean identities from it, where if I divide everything by sine squared, I'll get 1 plus cotangent squared equals cosecant squared. If I divide everything by cosine squared, I'm going to get tangent squared plus 1 equals secant squared, right? You get the idea. So, but everything comes from our sine squared plus cosine squared equals 1. All right. Our other property, second property, is sine and cosine are periodic functions, and their period is equal to 2 pi. Okay. So if I go back to this graph here, this was at 2 pi, right? So the time it takes to make 1 full circuit of my cycle, of my design, is 2 pi, right? And so then the next is going to be 4 pi. So it's going to go through the same design here. It's going to take, like, multiples of 2 pi are going to give me this chunk of design. Okay, so that's what it means when we talk about with period of 2 pi. So then, therefore, I can say that my sine of t is equal to the sine of t plus 2 pi k. Cosine of t equals the cosine of t plus 2 pi k, where k is an integer, right? So it basically gives us multiples of 2 pi, and that's equivalent to my sine function. It repeats itself. We're going around that circle again and again and again. Okay, our third set is that sine is an odd function. I don't mean sine's an odd function. I mean sine is an odd function, which has the property that odd functions have the property f of minus x equals minus f of x. Okay, where if I say sine of minus x equals minus sine of x, it also has a symmetry about the origin. The graph has a symmetry about the origin, right? If I look at my graph of my sine function, it's symmetric here about my origin. Okay, that's another defining feature for our odd functions. Our cosine is an even function. Our defining characteristic for even functions is f of minus x equals f of x. Right, so if I use that with cosine, okay, and that's basically like, it also has a symmetry about the y-axis. Even functions do, you can see the cosine function has this mirror, I can mirror reflect it around my y-axis. That's the symmetry on the y-axis, our graph. Okay, so sine's an odd function, cosine's an even function. These concepts come up again and again because they help us define other more complex ideas. Okay. I guess I'll have that before I turn the page. So our next property is what we call an angle addition formula. I think of this as an identity, but it's usually a lot of these things, these angle addition and double angle formulas are at the beginning or end of calculus books, trig books, pre-calculus books. You can find them there. So this is for all alpha and beta. Alpha and beta are angles. Okay, so I can say sine of alpha plus beta. These are 2 angles I'm adding together, but they're different from each other. It's going to be equal to the sine of alpha cosine of beta plus the sine of beta cosine of alpha. Cosine of alpha plus beta is going to be equal to cosine of alpha cosine of beta minus sine of alpha sine of beta. This is an addition formula. Okay, let's see. Double angle formula. Oops. This is when alpha is equal to beta. Okay, basically I'm plugging in alpha for here, so I get sine of 2 times alpha. Right, and so then what happens if this is sine of, it's be sine of alpha, right? You can just imagine, so this is going to be equal to 2 sine of alpha cosine of alpha. Okay, where alpha and beta are equal to each other. Do the same thing here, cosine of 2 alpha is equal to cosine squared of alpha minus sine squared of alpha. Now I can use the Pythagorean identity to substitute in for cosine squared or sine squared. So if I want this equation here to be just in terms of cosine or just in terms of sine, let's say 2 cosine squared alpha minus 1 equals 1 minus 2 sine squared alpha. These are equivalent. This is a square. Let me make that more obvious. That's a square and not a 2 alpha. Squared of alpha. Okay. So these are all equivalent. All I did, this is where it comes from our formula here. All I did was substitute in the Pythagorean identity and simplify it. This is if I want my formula to be in terms of one trig function. Okay. Sometimes you want that because you can simplify it with other things. Okay. Right, another property. So for all alpha, say sine of alpha equals cosine pi over 2 minus alpha. Cosine of alpha equals sine 2 minus alpha. What does this mean? This is basically like saying sine is equal to the cosine, but just shifted by pi over 2 by 90 degrees, right? Cosine is equal to the sine function, but just shifted by 90 degrees by pi over 2 radians. If we look at the graph, right, you can see the shape. Look, this is our red, this is our cosine. If I moved this over, right, this here, this distance between here, I didn't draw the amplitudes very well. They're the same amplitude. If I move this distance over, the red graph sits right on top of the blue graph, right? My cosine and sine are fundamentally equal to each other. They're just what they call phase shifted. They're shifted out of sync by pi over 2 radians. Okay, so I can shift them back and it'll be the same function. And that's all that we're saying right here. Okay. All right, let's do a quick review of special right triangles. They pop up again and again. So let's think, I'm gonna draw a little, here's my unit circle again. Oh, I'm not gonna draw a very good circle. X. Okay, so this is pi over 2, here's 0. Right, so this is, I've gone pi over 6 radians, pi over 4 radians, and pi over 3 radians. Okay, so you want to be able to visualize where these are in our unit as we traverse around the unit circle. So if I think about sine, what are the sine and cosine of these angles here? So this is my theta, say for example. So I'll say sine of t, cosine of t, and then the values that I want to take a look at are 0, pi over 6, pi over 4, pi over 3, and pi over 2. The joy about the unit circle is that these values repeat themselves as you progress around the circle, but just the signs, positive or negative, are going to change. So the sine of 0 is equal to 0. Cosine of 0 is equal to 1. That's right here, right? So I've gone out 1. That's my radius. So I've gone up 0 in my y direction. I've gone completely over 1 in my x direction. That's how you want to think about it. So then what's our x and y equal to here? So pi over 6, we've gone 1/2. Equal to radical 3 over 2. That's the value. So sine of pi over 6 is equal to 1/2. Cosine of pi over 6 is equal to radical 3 over 2. Pi over 4, multiples of pi over 4, that's where our sine and cosine are equal to each other. Okay, this is equivalent to our 45-degree angle, right? This is a complementary, pi over 6 and pi over 3 are complementary. right? So these, you can see these values are the same here. Now, pi over 2, we're up here on the axis. So my y value has its maximum and my x value has a minimum. Okay. Now these values repeat themselves as I progress around in the different quadrants, right? The values, the magnitudes themselves. But what happens is, right? So if cosine and sine are related to our x and y, cosine and sine are both positive in the first quadrant. Here in the second quadrant, the cosine's negative, but the sine's positive. Third quadrant, cosine's negative, sine's negative. Fourth quadrant, right? Cosine's positive, sine's negative. Okay, so these values here are the same, but just the positive and negative will be different depending on what quadrant you're in. So that's how you want to think about it. These values here, if I unwrap them and I plot them on a graph, right, I'm going to be able to build up my sine function. These are actual number values like along my amplitude here. So this would be like our pi over 2. This would be 3 pi over 2. Okay, and then 0, multiples of pi, 0 pi and 2 pi. So that's how you want to be thinking about how you're going to build up your sine function. Okay. All right, so let's talk about what happens as we approach some critical places, critical numbers. So if I think about my limit as t approaches 0 from the right-hand side of my sine function, right? So as I'm approaching from the right-hand side, my sine function is approaching 0. The limit is t approaches 0 from the left-hand side of my sine function, right? That's also approaching 0. So then I can put those together and say the limit as t approaches 0. It's the same, the limit's the same on both sides. The limit of sine of t equals 0. I can do the same thing for my cosine function. Not drawing that very well. All right, so I'm going to do that for my cosine. So the limit cosine, as we approach 0 from the right-hand side, that's equal to 1. The limit of our cosine function, as we approach 0 from the left-hand side, that's also equal to 1. So I can put them together. Right, and say this is what's happening. These are important pieces here. So I'll put that in a red block. As we approach 0, that's an important thing. We can, we talked about these functions earlier, but I'll just write it down here. So as t approaches 0, sine of t over t, it's a common function, that's equal to 1. Limit as t approaches 0, 1 minus the cosine of t over t, and that's equal to 0. And I'll put a red block around that. Okay. So we're going to use these ideas, these values here to help us answer more complex questions. Okay. Everybody have that before I turn the page? So let's talk about derivatives. So these are theorems, right? So if I want to, take the derivatives of my sine and cosine, right? What am I looking at? There. Okay, so now basically when I go to take the derivative of my sine of x, my first derivative of sine is equal to my cosine. When I go to take the derivative of my cosine function, okay, that's equal to minus the sine of x. Okay, watch your signs. They're positive, negative signs. So sine of x derivative is cosine. Cosine is sine, but this is a negative sign. This is a positive cosine. Okay, if you can't remember, think about your graph. Taking off from 0 signs an increasing function. That helps me remember, oh, this is positive cosine. Right, taking off from cosine, right, right from 0, my cosine is a decreasing function just at the beginning at 0, so it's a negative. Right. Also, when I go to do the second derivative of sine is the derivative of cosine. So this is going to be minus the sine of x. Take the second derivative of cosine. So I've got the minus that carries through, right? And then the derivative of sine is equal to cosine, right? So what happens is sine and cosine, because these are these functions that basically repeat themselves over and over and over and over again. They're a special class of functions like e to the x ln of x, they have an infinite number of derivatives. Okay, so I can keep taking derivatives all day long, right? But what happens, you'll notice, and we'll do this a lot in calculus too, you'll notice that the derivatives start to repeat themselves. So the third derivative looks different, but then by the fourth derivative, I'm back where I started from. Okay, so by the fourth derivative, my sine is equal to my first derivative. Same thing with cosine. So by the fourth derivative, we're back to where we started from. Okay, so back to our original function. So that's important because then when you go to derive, like in calculus 2, when you go to derive like an nth, derivative for sine or cosine, you basically know that, is it going to be, divisible by 4? Am I at the fourth derivative or am I at some other, derivative? I kind of have an idea about what's going to be happening. Okay. So also, we can say y equals sine of x and y equals cosine of x are solutions to the differential equation y double prime plus y equals 0. Right, so second derivative plus the function equals 0, right? Second derivative plus the function is going to be 0. Second derivative plus the function will be 0. Kind of knowing what these solutions are is going to help you when you go to do more complex things like differential equations and when you go to apply it later. All right, so I'm looking at lecture examples for chapter 2.7. We're just going to start rolling through examples now. We'll take derivatives and then we're going to apply it to a mass and spring problem, which is a common problem. Excuse me. So example number 1, we've got these two functions, right? So this z function applies to question A, w function applies to question B. So I want to find the derivative with respect to r on z equals r sine of 5 times r. So when I do this one, I've got r and sine of 5r. I'm going to be thinking about product rule and then also chain rule. And then here on this function here, I don't have a product rule, but I have my exponential rule, and I've got a chain rule that's happening that I need to think about. Okay, just kind of maybe take notes for yourself when you look at things like, okay, these are the different things I need to think about when I do it. So we go to take this one here. My product rule says I have to go first times the derivative of the second. So my derivative says I'm going to go cosine of 5r time, because that's the derivative of sine is cosine. So if I have a 5r, then I do cosine of 5r. It's the same thing. Now I have to do chain rule, which is times 5. Okay, plus the derivative of the first times the second. Okay. Now what we do is we're going to take this 5, we'll put it out front here, so it basically becomes an amplitude modulator for this. This is 5r cosine of 5r plus sine of 5r equals our derivative. Okay. Right, next function here. So e to the cosine of u. So w equals e to the cosine of u. So I want to find w prime. So now it's an exponential function. So I need to do what we always think about. I have to repeat my exponential cosine of u. Now I have to do the chain rule, which says take the derivative of what's inside, which is minus the sine of u. Okay. Put parentheses around it if you have a negative, because you don't want to confuse yourself and think you're subtracting it. Or you don't want to confuse the grader, whoever's grading your exams, to think you're actually subtracting these out. So put parentheses so it's obvious that you're multiplying. And now we can, well, actually we tend to put the negative out front. So minus e cosine of u becomes an amplitude for our sine, sine of u function. Okay. And then we're done with that one. All right, so let's go ahead. Example 2, we're taking a look at. So natural log of cosine of x. You could do u substitution if you want, where u is equal to cosine. Okay, so you would take 1 over u du is going to be your derivative. Okay, but I'm going to just jump right in. So this derivative, right, when I go to take that, is going to become 1 over cosine of x times, now I have to do the chain rule. My derivative of cosine is minus the sine of x. So you notice I put parentheses around it. Now I'm going to clean up some minus sine of x over cosine of x. Oh, Sine of x over cosine of x, that's another trig function. You're going to be expected to know that and put that in that form. So minus tangent of x. Yep. Okay, we've got two pieces here we're going to deal with. So let's take a look at each piece here. So when I do this, I've got the chain rule, right, with that 3x in there. I've got a chain rule I need to think about. And then sine of x over x, this is my quotient rule that I have to worry about. Okay, so let's take it piece by piece. So when I go to take that derivative, I'm looking at, let's do this part first. So I've got my coefficient I'm inheriting. I've got my chain rule, and I've got minus sine of 3x. Okay. Plus, our quotient rule says bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay. I'm going to put these together. So this is minus 15 sine of 3x plus, and I'll just leave it all as one piece, x cosine of x minus sine of x. And that's it. You don't have to bring them together into one. You just leave it. So far, so good? Anybody have questions on what we've done so far? Okay. So our last example is a mega example. It's gonna take us a while. It's gonna take us a while to work through it. Okay, but it's a good problem because there's a lot of different pieces to it. So we've got a mass and spring, and we're given an equation to talk about where's the position of the block, right? We've got this mass and I'm moving around. We're going to draw pictures so you can visualize. So we want to find the position, velocity, and acceleration of the block at two different time periods. And then we're going to find out, you know, where does it, I didn't actually write it down as a separate question, but where does it reach its maximum, you know, points at what time does it reach those? And then what happens to the block after a very, very, very long period of time, which is like another way of saying, let's take the limit as t goes to infinity, really long time period, okay? So first let's draw out some pictures so we can visualize what a mass and spring looks like in different stages. So first I'll draw the equilibrium, what it looks like. So I've got a wall, and I've got some kind of floor. We're dealing with a frictionless surface here. Example 4 takes this problem here and it adds friction to the floor. But for the first example, we're dealing with a frictionless surface. So this is our position. This is equilibrium is at 0. So at equilibrium, our mass, our block, is just sitting right here on that spot. And then the spring is just kind of relaxed. You know, there's nothing going on. When we move the mass out this way, we move it into a positive direction. When we compress the mass that way, it's in a negative direction. All right, let's draw out a compressed spring, see what it looks like. Okay, so here's our equilibrium position. Right, compressed spring is going to be where I've pushed the mass closer to the wall and my spring is a little bit tighter, kind of over exaggerated so you can imagine. Here's our positive direction, here's our negative direction. So I've pushed the spring right into the negative, it's compressing it. Push the mass, sorry, into that negative. And then let's do a stretched spring. Here's our wall. Here's our floor. Here's our equilibrium. Here's our mass. I'm going to try to exaggerate that I've stretched that out. Okay. So you can visualize like what it means when we say what's happening. All right, so let's just write down some points here. So there's no friction on the floor. I'm telling you that there's no friction on the floor. So the block is set into motion. So position of the block. Right, without friction, this block is just going to oscillate back and forth, right? There's nothing to slow it down. So it's just going to, once I set it in motion, it's going to stay. Okay, nothing to slow it down. And we were given the equation for the position. You can tell it's oscillatory because the cosine. Cosine function is going to describe that oscillation back and forth. Okay, so now we want to be able to figure out what's going on, position, acceleration, and velocity. So part A. So we're going to look at our position first. So this is given by x of t equals 2 cosine of 3t. So I'm going to look at my position at two different time periods, the time periods that they told me to look at. So at t equals 0, I'm going to plug in. So this is x of 0 equals 2 cosine of 3 times 0. So 3 times 0 is 0. Cosine of 0 is 1. 2 times 1. So this is just at 2. And I'm telling you it's in meters. I forgot to say the units. It's 2 meters. Okay, so this is 2 meters. It's a positive number, which means it's to the right of equilibrium. Okay, so t equals pi over 2. Let's take a look. What does that look like? X of pi over 2 equals 2 cosine of 3 pi over 2, right? Everywhere I see a t, I plug in a pi over 2 now. 3 pi over 2, that's right, that's on my y-axis. My cosine is equal to 0 at 3 pi over 2. So 2 times 0, this is at 0 meters. Right? So we're right at the equilibrium position. Okay. I can imagine, right, at time 0, I pulled it out. Okay, and then at time pi over 2, right, it's back at the 0 position. So that's position. Let's talk about velocity. So velocity is related to position by a derivative, right? So my velocity function is my derivative of my position. So I'm going to take the derivative of this position to get the velocity. So when I do that, remember we've got our chain rule. So I've got 2 times 3 times minus the sine of 3t. So I'll put that together. So this is going to look like minus 6 sine of 3t. Is our velocity. That's the equation I'm going to use when I answer questions about velocity. How fast is this going? All right, so t equals 0. We have 0 equals minus 6 sine of 3 times 0. Okay, so look at 3 times 0 is 0. Sine of 0 is equal to 0. So right at time t equals 0, we're going 0 meters per second. The t equals pi over 2. The velocity of pi over 2 equals minus 6 sine of 3 pi over 2. All right, let's think about it. So 3 times pi over 2, so 3 pi over 2, the sine of that is equal to minus 1. So this is minus 6 times minus 1, which makes it 6 meters per second. Okay. I'm going to turn the page, you guys. You all set with that? We need to do acceleration. So our acceleration, a of t, is the derivative of our velocity. Okay, so when I go to do the derivative of the velocity, again, I've got my chain rule. So minus 6 times 3 times the cosine of 3t. So I'm looking at e of t is equal to minus 18 cosine of 3t. So that's the equation I'm going to be working with. t equals 0. E of 0 equals minus 18 cosine of 3 times 0. Right, so cosine of 0 is 1 times minus 18. It's going to give me minus 18 meters per second squared. Okay, time t equals 0, my acceleration is negative. Okay. T equals pi over 2. We're going to talk about what this means all in a minute. Okay, so minus 18 cosine of 3 pi over 2 is equal to 0 meters per second squared. Okay. Right, I've gone minus 18 to 0. So this is kind of telling me a couple things. So my block must have changed direction between t equals 0 and t equals pi over 2. At t equals 0, our block was to the right of our equilibrium point. And it stopped. It was accelerating to the left, right? That's what this means. It stopped, but it's accelerating to the left. Okay. So at t equals pi over 2, our block, our mass, is in the equilibrium position, but it is moving to the right. So it's changed direction somehow. So we want to be able to figure out, like, at what time is it changing direction? So what time does it reach its maximum? So our question is, when does the block reach its maximum displacements to the left and right? Right? So we start in equilibrium, we pull it out, and we let it go. Right? At what time does it actually reach these maximums? So it gets to here and then it turns around. So we want to be able to figure out, when does that reach that spot? So what we're really asking is, when does our position function have a local max or a min? So we're looking for critical points, right? This is a critical point question, which means I need to take my derivative and set it equal to 0 and then solve for t, right? So my derivative of position is my velocity. Okay, so where my velocity is equal to 0. So I'm going to plug that in. That's minus 6 sine of 3t. So I get rid of the minus 6. So I'm going to go sine of 3t equals 0. So the question I have to ask myself is, at what time t does the sine equal to 0? What angle t will my sine be equal to 0? Right, and that happens when this is equal to 0 and pi. So 3t equals 0 and 3t equals pi, right? Because my sine function, right, think about your unit circle again, right? My sine function is 0 at 0 radians, and it's 0 again at pi radians. So now I solve for t, oops, sorry. So t equals 0 and t equals pi over 3. So it's periodic, so multiples of this will make it, I'm going to be able to figure out, so multiples of pi over 3 are going to give me my max and min. All right, let's do our check. So I'm going to check my position at 0. We did this at the beginning. 2 cosine of 3 times 0 gives me 2 meters. And then I'm going to check my position at pi over 3 to find out what is the position, right? What's the position? We found out the time when it's happening, but what's the position? What is our maximum displacement? 2 cosine of 3 times pi over 3. So 3 times pi over 3 is pi. Cosine of pi is minus 1. So 2 times minus 1 is equal to minus 2 meters. So basically what's happening is, right, we pull our block out to 2 meters and we let it go, and it goes 2 meters, minus 2 meters, 2 meters, minus 2 meters. And it just oscillates back and forth between these max and min, okay? Because there's no friction on the floor. Okay, so, oh, and then, so let's write this down. So the time it takes to go through 1 oscillation is equal to the period. And we call that big T. And also you hear things in terms of frequencies, so 1 over the period is your frequency. We were asked part B, I'll let you guys finish writing that. Part B says, what happens after a very, very long time? Okay, so let's answer part B. What happens after a very, very long time? Okay, I'm basically taking the limit t goes to infinity of 2 cosine of 3t. Okay, so when I do this, right, we kind of saw this before, right? So what happens to this? This cosine function has an amplitude of 2, so it's going to be oscillating from 2 minus 2, 2 minus 2, 2 minus 2 forever. It's equal to okay, so it's just going to oscillate between positive 2 and negative 2 forever. Because there's no friction on the floor to slow it down, right? Which is our next example. Example 4 says we're going to add a friction element to this, right? Okay, so let's add some friction. So the floor, right, we've got this 2, I'm taking the 2 part, and I'm attaching it to the e to the minus t. So cosine of 3t now is our oscillatory force, right? Oscillatory position. And then 2e to the minus t basically tells us what it, the friction. So here's our x and our y. I'm going to graph this out. It helps to graph, you can kind of visualize. So here's our e function, and our cosine function oscillates, bounces between these. This becomes an amplitude modulator. All right, so this is our position. So let's do the same thing again, but now we've got an amplitude that's basically making our oscillations dampened. Okay, so let's take a look. So our position, right, which is this function right here. So I'm going to go at t equals 0. What happens? So x of 0 equals 2e to the 0 cosine of 3 times 0. This is equal to, again, 2 meters, right? E to the 0 is equal to 1. Cosine of 0 is equal to 1. T equals pi over 2. Right, so this is going to be 2e to the minus pi over 2 cosine of 3 pi over 2. So again, cosine of 3 pi over 2 is equal to 0, so that dominates. So we're at 0. Let's take a look at our velocity. Okay, remember velocity, now to get the derivative, I'm going to need the product rule. Right, because I've got e to the minus t as one function and cosine of 3t as the other function. So I need my product rule. So to get my velocity, okay, I'm going to write it out. I have to do the first. I did 2e to the minus t as my first function. First times the derivative of the second plus the second times the derivative of the first. It's going to give me minus 6e to the minus t sine of 3t minus 2e to the minus t cosine of 3t. Okay. That gives me my velocity function that I'm going to then plug into. E equals 0. So velocity at 0 is minus 6e to the 0 sine of 3 times 0 minus 2e to the 0 cosine of 3 times 0. This goes to 0, right? And this is minus 2 meters per second. Okay. At pi over 2, what's happening? I'm going to plug pi over 2 in, so I'm going to get minus 6e to the minus pi over 2 sine of 3 pi over 2 minus 2e to the minus pi over 2 cosine of 3 pi over 2. Okay, cosine of 3 pi over 2, this goes to 0. 3 pi over 2, this is a minus 1, right? This is a number now, so I've got minus 6 times minus 1 times e to the minus pi over 2. So this becomes 6e to the minus pi over 2 meters per second, which is, if I multiply e to the minus pi over 2, it's just a number, and I can plug it into my calculator. Make sure you use the pi button. When I plugged it in, it was roughly equal to 1.247 meters per second, which is different than what we saw before. Okay, so this is already, we're changing. All right, now acceleration. Okay, so now to get acceleration, I have to take the derivative of my velocity, but watch out. I've got two terms, and I have to do the product rule minus the product rule. So I've got, it's gonna, you know, these things that get more complex as we go. I'm gonna give you just my answer for it. When I did it, I got minus 18e to the minus t cosine of 3t plus 6e to the minus t sine of 3t plus 6e to the minus t. I can combine these, but I didn't. Plus 2e to the minus t cosine of 3t. I could have combined them, but I didn't. All right, so now let's take a look. T equals 0. Okay, so at time 0, I've got minus 18e to the 0 cosine 3 times 0 plus 6e to the 0 sine of 3 times 0, 6e to the 0 sine of 3 times 0 plus 2e to the 0 cosine of 3 times 0. Okay, sine of 0, that goes to 0, sine of 0 goes to 0. So I've got minus 18 plus 2, right, which is going to give me equals minus 16 meters per second squared. Okay, at time t equals 0. Okay, let's take a look. T equals pi over 2. At this point, right, I'm just plugging it in and then taking a look at what's my sine and cosine. Okay, pi over 2 equals, I'm just going to plug it in. Everywhere I see a t, I plug in a pi over 2. Minus 18e to the minus pi over 2 cosine of 3 pi over 2 plus 6e to the minus pi over 2 sine of 3 pi over 2 plus 6e to the minus pi over 2 sine of 3 pi over 2. It takes forever to write this out. Plus 2e to the minus pi over 2 cosine of 3 pi over 2. Okay, 3 pi over 2 cosine, that's equal to 0. This is 0. This is 0. 6, this is minus 1. That's minus 1, right? So now when I do this, I'm going to get minus 6e to the minus pi over 2 minus 6e to the minus pi over 2, right? Because it's these sine functions here. It gives me minus 12e to the minus pi over 2 meters per second. Okay, and this was like approximately equal to minus 2.49 meters per second squared. Sorry, there's a squared in there. Okay. All right, let's ask ourselves, phew, this is a lot of work, right? Let's ask ourselves what's happening, okay, as we go out towards infinity. You guys got this? I'm gonna turn the page. I realize there's a lot of math, there's a lot of stuff going on here, but it's all based on the things that we've been doing so far, right? We've got the product rule, okay, and I've got, you know, multiple pieces that I need to put together. Take your time when you're doing this stuff, and then make sure you keep track of all the pieces, okay? And then, like, you can see how we're just spelling everything out. We're just plugging things in and we're working it through. Okay, take your time. Okay, so now let's take a look where we say, what happens after a long period of time? Okay, so this is part B. So that means I'm going to take the limit as t goes to infinity of 2e to the minus t cosine of 3t. This is my position. What's my position after a long period of time? Okay, so I'm going to rewrite this limit t goes to infinity. That's going to be, I could put the 2 out front, cosine of 3t over e to the t. I do this to help me because the 2 is just going to be a multiplier on things, and then I brought the e down here to help me think about like what's happening as t goes to infinity, right? So I'm going to take a look at different pieces. So the limit as t goes to infinity of my cosine of 3t, right? This thing oscillates. right? We did that before, we talked about that. And now the limit as t goes to infinity of 1 over e to the t, right? That's this piece right here. So 1 over e to the t, let's think about that one. E to the t, e to the infinity is a huge number, right? E to the 10 trillion, huge number. 1 over a huge number is a super duper small number, so this thing goes to 0, right? So if I put it all together, so the limit goes to infinity of 1 over e to the t times cosine of 3t, and then there's a 2 multiplying. This oscillates, but this goes to 0, so this whole thing is going to go to 0. So this is like what we graphed out at the beginning. Excuse me. Right, so here's our e to the x function, and our cosine function gets dampened. After a very, very, very long period of time, this thing does that. Right, you pull the spring out, and it oscillates back and forth, but because of the friction on the floor, it ultimately just, comes back to equilibrium. Okay. Okay. And that's 2.7, sine cosine. So we took things that were fairly basic, and now we are applying them to describe a more complex problem. We have a few minutes. If anybody has any questions, I'd be happy to talk about homework problems or whatnot. We have about like 5 minutes before the end. If you guys, I put up a whole bunch of homework solutions, detailed solutions up online yesterday on this week's module. If you want to take a look at those, that'll help you. Any other questions on homework? If you guys don't have questions on homework, then we can end class a few minutes early. I'll scan this in later today and then put that up online. 2.5, number 25. Did I put that up? No, I didn't. Okay, so give me a sec. The question was 2.5, number 25. Okay, let me take a look. Where's my 25? Is that? Okay. So this is homework, chapter 2.5, question number 25. So what I have is g of t equals 1/2 t to the -1 minus ln of t. And then we're asked to find the derivative of that. So then g prime of t, right? I'm just going to work it through. So g prime, so the power rule on here says minus 1/2 t to the -2. And then the derivative of ln is 1 over t. Now the second derivative, I'm going to do the power rule again. So this gives me, we can make it just 1, so this is t to the -3, and this becomes plus 1 over t squared. And then we're setting that equal to 0. So I took that derivative, right? So it's going to be negative, but then there's a negative there already. So I took that derivative, set it equal to 0, and I get minus t to the -3 equals 1 over, t squared. So I get minus 1 over t cubed equals 1 over t squared, which gives me minus t cubed equals t squared. Okay. Basically, I'm looking at minus t equals 1, so t equals -1. Now what happens is, this is a problem, right? So technically speaking, this looks like it should be an inflection point, right? This is the way that we've solved it. We get this point here, but when I go back to my original function here, my function is undefined. Okay, at this point, t equals -1, my function is undefined. I can't do ln of minus t. So therefore, it's not an inflection point. I think the whole point of a question like this is, okay, so you're doing all the algebra, right? And you get some number, but you got to go back and check to see, is that like a domain restriction? So this value here right, isn't allowed on the domain. So it actually is technically not an inflection point because it's not allowed on the domain of our function. Okay. Does that make sense? Hey guys, I'll have office hours today at 1 o'clock. And don't forget your homeworks are due tonight at midnight, and we have a quiz that opens up at noon today, which will be open for 24 hours. Okay, and that'll be 2.4 and 2.5 on the quiz and the homework. Okay, guys, have a great day.
Bye. Thank you.
Thank you.
Take care.
Thank you.
Bye bye. Thanks.
Thank you.